margin. Okay, Nicole is here. And Miguel. Okay, here's Johnny. Colton, Justin, Rosa, excellent, and KB. Let's see, and then there's. Okay, did Roy come in? I don't think Roy's here yet. Okay, there's the Eric. Wait just a little bit longer. Okay, I just checked. Roy actually has an unexcused absence. I mean, not unexcused, an excused absence. So we don't need to wait for him. All right. So the title of this chapter is Nonlinear Functions. And so although we spent a lot of time working on quadratics, that isn't the only nonlinear function that we were, intending to look at. Some of our problems had inverse variation problems in it. So nonlinear just means it's not a line. It's some type of curve. And there are a lot of different types of curves that we could study. But this last section, lesson 3 in our chapter, is about logarithms. The inverse of exponents. And so I don't know if you've ever, if you have thought about it, we've studied exponential equations quite a bit, in eighth grade, I'm sure you did. Well, in course 1, and then maybe even in 7th grade. If you were in the, advanced class, you might have had exponential type equations. But this is just as a reminder, I'm just leading up to our topic, okay? So if you have an expression that looks like this, say 3 to the x power plus 4. Well, no, I'd have to put a number in here, say 7, okay? And you wanted to solve for x. If your variable is an exponent and you want to solve for that, we never have solved those algebraically up to this point. If we had to solve an equation like that, we would just use our calculator and make a table, look in the y column for the 7, and then look over in the x column to find what the x value was, because the only way you can solve an equation like this is to use logarithms. And so now today's your lucky day, because this is when we start learning about logarithms and how to use them to solve exponential equations. Right, so buckle your seatbelts. This is really exciting. Okay, I love logarithms. I really do. Logarithms is the world of the exponentially small. I mean, no, not exponentially, infinitely small, because this is how we can express numbers that have, 50 zeros and then 7 5s. Okay, you can express that as a logarithm in a much easier way. So it's used a lot in the sciences where we deal with these infinitely small, amounts. that rather than writing all those, all those zeros like that, why not just express it as a logarithm? Okay, so that there are a lot of applications for this if you go in certain fields. All right, not so if you're going into the sciences, you'll see as a career, you'll see a lot of logarithms. So let me present our document for today, because that has a lot of information in it that I want to refer to. All right, so we have this table of values here. And, okay, yeah, I've got my equations up here. Now, in the middle are items that create sound, okay? Like a military rifle, a jet plane, a level at which sound is painful. Here's an amplified rock music, power tools, a noisy kitchen, heavy traffic. These are all things in our world that generate sound. And so what this table gives you is how the intensity of that sound is typically measured. All right. So here is the intensity of this sound, of these sounds, represented as exponential expressions of 10. Okay, so the units of sound intensity are watts per centimeter squared. Okay, so this, and these all represent values. I mean, we could, 10, I'm having a little trouble reading that. 10 cubed, that's 1,000. Okay, if you want to put a number to it. And so 1,000 watts per centimeter squared, that's how you measure the intensity of the sound that a military rifle makes. And so this goes in descending order: 10 squared, 10 to the first, 10 to the 0. Then we get into negative exponents too. These are numbers that are really, really small. So something that's barely audible, 10 to the negative 12, that's a decimal, with 12, I think 11 zeros and then a 1 at the end. Okay, an extremely small number to measure the intensity of the sound that is barely audible. Okay, now look over here in this column. This is another way that we measure sound intensity. We call this relative intensity, and it's measured in different units called decibels. And so these are, you can just see the decibel levels. Of course, starting from the most intense sound down to something that's barely audible, we could call that, it has 0 decibels. All right. Now, look up here on the board, because this is given in the book. All right. Intensity is measured with this expression, 10 to the x. And we've seen those type expressions here, except I filled in the exponent is filled in for you. Okay, now, if I took that same x value here and I plugged it into this equation, 10 times x plus 120, that would calculate the equivalent decibels. Okay, so let's see if this works. If I, for a military rifle, 10 cubed, okay, equals 1,000. Okay, so 1,000 watts per square centimeter. That would be the measure of the intensity of a military rifle. Now, if I take that exponent, 3, and I plug it in here, 10 times 3 plus 120, that equals 150. That's now, these are not supposed to be equal to each other. They're not. It's just two different ways of measuring sound. So this one has, a military rifle has, 1,000 watts per square centimeters in terms of sound. And then if I take that 3 and I plug it into this equation, it calculates the 150 decibels, which is the relative intensity of a military rifle. All right, so just I'm going to use this context on some of the problems that we're going to do. So I'm just trying to give you, a little bit of background information on this. Okay, so now, well, I'll leave these equations up here, and then we are going to go to, all right, now this, let's see, do I need this document? There's nothing else in this document that I really need. I just wanted to introduce the two equations for the different ways to measure intensity, and, showing you how, just these table of values, and how they're not supposed to be equal. Like 10 cubed does not equal 150. That's not the point. But you can use that exponent to calculate the number of decibels using these two formulas. All right. So I'll show you how logarithms is going to come into play here. All right. So I think I don't need this document anymore. So I think I'm just going to go ahead and stop sharing that. And all right. Now on number one, what they've done on number one, this is in your book. Let me see. It is, oh gosh, let me get a page number here. I'm on page 379 in the textbook, if you like to follow along in the textbook. But the directions in number one are express each of the numbers in part one as powers of 10. Okay, so express each of these numbers as 10 to some exponent, okay? You can find exact values for some of the required exponents by thinking about the meaning of positive and negative exponents. All right, so we'll start out real easy, okay? If you wanted to express that as a power of 10, how would you express that? This would equal 10 to the what power?
Power of 2.
Power of 2, right. 10 squared equals 100. Okay, so let's go up to 1,000 so you can see the pattern. All right, no, 10,000, sorry. All right, that's going to be 10 to the what?
Power of 4.
To the power of 4, because that just means you're multiplying 10 by itself 4 times. 10 times 10 times 10 times 10. And you know this trick. When you multiply a number like 10 times itself, you just count the zeros. All right. So the number of zeros in this case is the exponent. All right. So that's the one pattern they can look at here. Okay. So what about 1 million? That would be 10 to the what?
6.
Yeah, 6. Okay. So 10 multiplied by itself 6 times is going to give you 1 million. All right. Thus illustrating the convenience of this type notation when you're writing very, very large numbers. All right. So now on D, what we want to do is we want to get smaller. All right. So let me illustrate something for you. If 100 is 10 squared, then 10 is going to be 10 to the first, okay? And 1, okay, no zeros at all, is going to be 10 to the 0, right? You see the pattern? So I went from 100 equals 10 squared. 10 is 10 to the first. 1 is 10 to the 0. Okay, so if I went 0.1, follow the pattern, 2 to 1 to 0, what would that exponent be?
-1. -1.
To the what?
-1.
To the -1, okay? And so now, if I go Now, this is D, okay? So I just wanted you to see the pattern. Now I want to go 0.01. That would be 10. Just follow the pattern. What would that be? 10 to the what?
-2.
-2. Right. So, and if I move the decimal over one more place, it would be -3. One more place, it would be -4. Okay. So then this illustrates nicely how we can use powers to represent very small numbers. Okay. It just means your exponents are negative. All right. So now E, be careful now. -0.001. Okay. 10 to the what power? Now think about this. Is it possible to raise 10 to some power and get a negative number? I mean, you could experiment on your calculator. I mean, it's a small number. Seems like the exponent would be negative. But, you know, you can just enter some numbers, 10 to the -2, 10 to the -3, 10 to the -4. You know, look at the type of numbers that you're getting. When you do that, is your value ever negative? I mean, your exponent could be negative, but is the value of that power ever negative? You know, does it look like, is that even possible? Are you playing with it on your calculator? Okay, I have a different idea. Go to y equals. Let's look at a graph, okay? And let's just enter. Go to your y equals and enter 10 to the x. Now, I've got to give you a window. All right, so this will, let's let our window be from -3 to +3 and go up by ones. And then we'll go from, let me see. Okay, -50 to 360 and go up by 50. Oh, I said 360 instead of 360. Oh, well, that's all right. So let that be your window. Graph, just put 10 to the x in your y equals, and just look at the graph and see if that graph ever takes on a negative value. Not for x, for y. Does it ever have a y value that is negative? Does everyone have that window? You may remember what exponentially graphs look like. I mean, we haven't studied them this year. We are, I think we are later, maybe. I can't remember if we do or not. But is your graph looking kind of like that? It should. Okay. Does this graph ever go down here where the y values are negative? See, these are all the negative y values. See how it's always above the x-axis? You see? So it doesn't matter what I raise that 10 to, what power, what exponent I raise that 10 to, it will never take on a negative value. Okay? And you can see that clearly in the graph. Okay, so you would write not possible. Right? Okay, now let's do a different type of problem. Okay. I'll come up here on F. Now, what we're trying to find is 3.45 equals 10 to some power. Okay, now let's think about this logically. You know that 10 to the 0 equals 1, and 10 to the first power equals 10. So does it make sense that this exponent, because 3.45 is between 1 and 10, that the exponent is going to have to be somewhere between 0 and 1? Okay, so now we're getting into decimal exponents. So, okay, just start in the middle. 0.5, halfway between 0 and 1. Do 10 to the 0.5. Just use some trial and error. See how close you can get to 3.45. Just do it on your home screen. And if you want to get closer to it, you know, like maybe you're too small, try 10 to the 0.6 or 10 to the 0.4. And if you want to get closer, then do like add decimal places. If it, to what you know, if you think it's 10 to the 0.4 something, do 10 to the 0.45, 10 to the 0.456, 10 to the point, you know, and that those aren't the answers, but experiment like that and see if you can come up with something that's reasonably close. You might not hit it exactly. See if you can come up with a decimal.
I got 0.538, and that's really right on it.
Is that pretty close?
Mm-hmm.
Okay. So just by using trial and error, did you say 0.538? Or just 0.53?
538.
38, okay. All right, just using trial and error. So see, now we're in the world of decimal exponents, okay? Negative. So we already know we can have negatives. And now, if it's not some nice, neat number, like some multiple of 10, yeah, we're going to have decimal exponents, all right? So now, okay, so we got that. Now, G is going to be a giveaway now. It's negative 34.5 equals 10 to some exponent. Okay, now what did we just learn? Is that even possible? See, remember that graph of 10 to the x? It never goes below the x-axis, okay? So this is not possible. You can't raise 10 to a power and get a negative number. Okay, so now let's do 345. I'm just moving the decimal place, okay? 345 equals 10 to some power, okay? 10 to the x. Now, you know that 10 squared is 100, and you know that 10 cubed is 1,000, okay? And so since 345 is between 100 and 1,000, then you know it's got to be, the exponent's got to be between 2 and 3. Okay. So see, it's going to be 2 point something because it's got to be bigger than 2. So play with the numbers and see, it's going to be 2 point something. It's going to get you up to 345.
I got it.
What'd you get?
2.538.
Yeah, because look, we already had this, and we know it would be 3.45. So if you just move the decimal over, you know, to 345, so that's going to be 10 to the 2.538. So using a little bit of what we already knew there. All right. Okay, so And then, okay, I think that's enough of that. There's another one, but there, I think you get the picture, okay? That now our exponents can be any number. They're not always nice, friendly integers, okay? Now, let's go back on number 2. All right, so hopefully you've got all those examples down. Now, on number 2, let's go back to these 2 equations. Let's say that the intensity of a screaming baby is 9.5 watts per square centimeter, okay? Per centimeter squared, okay? Now, we want to express this as a power of 10. All right, so this is what we're trying to, this is a 10a. All right, so we want 9.5 to be equal to some power of 10. So let's use that same strategy we were just using. You know that 10 to the 0 equals 1, and you know that 10 to the first equals 10. Okay, so let me write this the other way so that it's all in the same order. I'll say 10 to the x equals 9.5. Okay, well, 9.5 is between 1 and 10, right? But it's a whole lot closer to 10 than it is to 1. So my exponent is going to be between 0 and 1, but probably a whole lot closer to 1 because 9.5 is closer to 1. Okay, so use that as a clue. You know, you don't want to start at 10 to the 0.1. All right, don't do that, or because you're going to be too close to the value of 1. Start up here, like at 0.7 or 0.8, where you're closer to the value of 1, and see if you can figure out what that exponent would be. Okay, what do we have? Okay, 9.978. Okay, so try that. Everybody try that, 0.978. See if you get pretty close to 0.5. You know, so, no, I'm sorry, 9.5. And that's what we guessed just using our reasoning skills. You know, we know this is true. We know this is true. But this number's a whole lot closer to 10 than it is to 1, so the exponent would be closer to 1. All right, and sure enough, it is. Yeah, 0.978, just using trial and error. All right, so that whole discussion, you know, and coming up with the exponent itself is that's A and B together. And now what we want to do on C is, since we know what how to measure the intensity, we would say the intensity is 10 to the 0.978 watts per square centimeter. Now we can calculate the decibels too, because we know what the X value is. So we can take that X, plug it in here, and we can calculate the decibels for a screaming baby. Okay? So I know that's just exactly what you wanted to do, to know today. Now, you know what? Let's, oh, no, we can use 978, okay, equals approximately 9.5. Okay? So now, take your exponent and plug it into this equation right here. 10 times 0.978 plus 120, and calculate your decibels. You want to have that? Just give me one decimal place. Emos?
129.78.
129.78. We'll give it 2 decimal places. Okay, this is decibels. And this number is watts per centimeters squared. It's just 2 different ways of measuring sound intensity. All right, but this is the connection between the two. The X value here, you know, the watts per square centimeter, you can express it as a number, but you could then, if you're willing to express that number as a power of 10, then the exponent can be used in this equation to figure out the equivalent decibel level. Okay, let's try this one more time. A TV that you have on really loudly has an intensity of 6.2 watts per centimeter squared. Okay, so figure out how you could express this number as a power of 10. Okay, this same idea exists. You know, it's gonna, 6.2 is between 1 and 10, so its exponent is gonna be between 0 and 1. So play with the numbers, see if you can come up with the exponent, and then calculate its decibels. That's like a TV, like just maybe at an audible level that, you know, would be reasonable for anyone to watch. You know it's going to be less than 0.9. You know it's going to be smaller, a decimal smaller than that. Probably between 0.5 and 0.9, somewhere in there. Come on. I got other fish to fry. Come on, we gotta go. What's this? What's that exponent going to be?
1.793. That's the closest I got.
Okay, it can't have a 1 in front. Okay, it should be just 0.79. Did you have a? Did you say 1.7?
Oh, is it 62 or 6.2?
Oh, yes.
I put
sorry.
62. Oh, I was going
6.2, but that explains that relationship too. You know, if I move the decimal over, you just put a 1 in front. Okay, but I'm sorry, that wasn't very dark. Okay, so 6.2 is going to be 0.79. So now when you plug in the 0.79 over here, because this X is going to be that same X value, then you should get about 127.9 decibels, calculating that. Okay, so that, you know, explains the relationship between, you know, how you can calculate these different sound intensities. Okay, now we're going to come back to this idea tomorrow, and it's logarithms are going to come up. But what I have to explain first to you is the definition of a logarithm. And let's practice with that for a little bit. Okay, so this is number 2. And now, okay, we don't need this anymore. We'll come back to that tomorrow when we finish up the investigation. But, okay, so if I have 10 to the b equals some value of a, right? Now, this is only when your base number is 10. You know, we're only learning base 10 logarithms in this class. Okay, now logarithms can have any base, but we're just starting easy, and we're just using base 10 in course 2. Okay, well, if you want to figure out what b is, then what you have to do is, the only way you can isolate b is to take the base 10 log of a. And you can look on your calculator. You have a log button. Look on the left, log. So find that on your calculator. So notice this. The base on the exponent is the same as the base. This is the base of your log. All right? And this is red, the base 10 log of A. And what you need to remember is that a logarithm is an exponent. See? See the exponent? The logarithm is the exponent. So if you take the base here, goes here, the base 10 log of this number in this position is going to give you that exponent. Now you write that down. Even if it doesn't make any sense to you, you write that down and it's going to make sense to you in a couple of minutes. Okay, we just got to put some numbers in and you'll see how it works. Now, right now on your calculator, I want you to hit the log button and enter the number 100 and then hit enter and see what it gives you. Let me get my calculator out too. Do you all see the log button on the left? Okay, just hit log 100, close your parentheses and hit enter. What do you get?
2.
2, exactly. This equals 2. Now here's one other thing that I have to explain to you. I'm going to move this over just a little bit. Log, I know I didn't write the base 10 in there, but base 10 is so common in the world of logarithms that it's actually called the common log. And so in any math textbook or on a test or a quiz or anything, if your logarithm is written like that, it's automatically base 10. Okay? You do not have to write the 10 in there. Now, if I had an expression like 2 to the x equals 17, okay, then my log would be base 2, because see, the 2 on the exponent, the base on the exponent is the base on the log, okay? That would equal x. But everything we do for the next 2 days is going to be base 10. We're not using, I just want you to know that logs can be any base, just like an exponent can have any base, all right? But we're going to stay totally in base 10 for the next few days. You'll learn the other bases when you get to course 3. Okay, we're just keeping it simple for while we start out. Okay, now the reason why the base 10 log of 100 is 2 is because 10, see, I told you this is an exponent. This base to this exponent equals 100. Now that you know 10 squared is 100. Okay, so connecting this to something that you are comfortable with is going to help you understand the logarithm. But if I didn't know what that was, if that was a mystery, okay, then all I would have to do is take the base 10 logarithm of this number, and it's going to give me the exponent. Okay?
So if that's the case, then for like hypothetically, if the log base was 7 and it was 49, would it still give you 2?
Okay, so 7 squared equals 49, right? Mm-hmm. So that means that the base 7 log of 49 equals 2. Absolutely. Yeah. Uh-huh. All right, so let's do a couple more. So B, let's see, we're doing the exact problems that we did in number 1. The log of 10,000. Just do that on your calculator. What do you get? Come on, it should take 1 second. Yeah, 4. And the reason why it's 4 is because 10, see the base, 10 to the exponent, 4 equals 10,000. That's why that logarithm is true. And you're going to have a homework problem that, you know, they're going to give you some expressions like this, and they're going to say, why is that true? Why is this true? And it's because of this. It's because of the definition of a log. This is true because 10 squared equals 100. Okay, so let's try C. Let's just keep going till the bell rings, okay? Let's, you know what? I'm going to skip around a little bit so we can do ones that aren't quite so obvious. Let's do D, the base 10 log of 0.01. Now, we figured that out up in number 1, but do it on your calculator now.
-2.
Yeah, you get -2. It's because 10 to the -2 equals 0.01. That's why that's true. All right, let's do this one. You'll see what happens when you try to take the log of a negative number. Okay, do that.
Error.
Error. You're going to get an error message. You cannot take the log of a negative because there is no value that you can raise 10 to and get a negative number, much less that one. It doesn't exist. Okay, that's why you'll always get an error message if you try to take the log of a negative number. Okay, let's do one that we had to kind of guess at, but we did a pretty good job of it. Log of 3.45. Do that on your calculator.
.537.
Yeah, 0.537. And probably the decimal goes on a lot further. You know, you have to cut it off at some point. And that's what we guessed. I think it was 0.538 because 10 to the 0.537 equals 3.45. So now we don't have to guess anymore. Now we got a calculator to figure out we can use logarithms to figure out those decimal exponents. All right. And then, okay, our bell's going to ring in just a second. Let's do this one. Okay, let's skip over. Let's do I. Okay, I'll put it up here. I do the log of 0.0023. This is the base 10 log of 0.0023. Get that number. What do you get? It's going to be negative something. Log of 0.0023. What do you get?
-2.638.
0.638. Okay, what that means is that if you raise 10 to the -2.638, it's going to give you 0.0023. Try that. Do that on your home screen. 10 to the -2.638 and see if you get something pretty close to that. I mean, it's all kind of approximations because it's rounded decimals, but you should get pretty close to it. All right, so number 4 in this is just the idea that you can't take the log of a negative number. We've already discussed that. But my intent was to get through number 4, and so that should be enough for you to do your homework tonight. Okay, that just deal with these issues that we've talked about here, and then we'll carry this further tomorrow. Okay. Bye-bye.
Bye.